Hello everyone. Welcome back to your class 11 math series. Today, we're stepping into one of the most powerful modern views of probability, the axiomatic approach. Now, have you ever wondered, how do we assign probabilities when outcomes aren't equally likely? For instance, in a cricket match, can we really say the chance of India winning and losing is 50-50? Of course not. That's where the axiomatic approach, introduced by the great mathematician Andrei Kolmogorov in 1933, changed the game. Instead of guessing or depending on fairness, we define probability using set theory and logical rules called axioms. So from the traditional coin and dice world, we now move to a universal mathematical framework where every event can be measured consistently and precisely. Let's define things clearly. Every random experiment has a sample space, denoted by capital S. It is the set of all possible outcomes. Each subset of S, denoted by E, is called an event. We define a function P, known as the probability function, which assigns a number between 0 and 1 to every event E. So we write P of E is greater than or equal to 0 and P of S equals 1. This means the entire sample space always has probability 1, while an impossible event has probability 0. Now comes an important rule. When two or more events cannot occur together, known as mutually exclusive events, their probabilities can simply be added. So for such events E1, E2, and E3, P of E1 union E to union E3 equals P of E1 plus P of E2 plus P of E3. This is the strength of the axiomatic method. It provides universal rules that work in every situation, whether the outcomes are fair or not. Now let's look at the three axioms of probability, step by step. Axiom 1. The probability of any event A is always non-negative. In symbols, we write P of A is greater than or equal to 0. Axiom 2. The probability of the sure event, that is, the entire sample space S, is equal to 1. So we write P of S equals 1. Axiom 3. If we have several mutually exclusive events A1, A2, and so on, meaning they cannot occur together, then the probability of the union is the sum of their individual probabilities. In symbols, P of A1 union A to union ... equals P of A1 plus P of A2 plus ... From just these three axioms, we can derive many useful results. For example, P of the empty set equals 0 and P of a complement equals 1 minus P of A. Pretty elegant, right? These three simple statements form the entire foundation of probability theory. Let's now use these axioms to derive some important and practical relationships. From axiom 3, for any two events A and B, we can obtain the addition theorem. P of a union B equals P of a plus P of B minus P of a intersection B. That small subtraction at the end is crucial. It corrects the double counting of outcomes that belong to both A and B. Next, if event A is a subset of event B, meaning it always occurs whenever B occurs, then P of A is less than or equal to P of B. And for complementary events A and a dash, we have P of a plus P of a dash equals 1. This means if the probability of an event is known, the probability of its complement is automatically determined. So whether you're calculating chances of rain or drawing cards from a deck, these relationships ensure your probabilities remain logically consistent and mathematically sound. In the classical definition of probability, we assume that every outcome is equally likely, like tossing a fair coin. In that case, the probability of an event E is given by P of E equals N of E divided by N of S, the number of favorable outcomes divided by the total number of possible outcomes. But what happens when the outcomes are not equally likely? For example, when a biased coin lands on heads more often. In such cases, the classical formula no longer works. This is where the axiomatic model comes to the rescue. It allows us to assign different probabilities to each outcome, as long as the total adds up to 1. For instance, if a coin has P of H equals 0.6 and P of T equals 0.4, then P of H plus P of T equals 1. So the model is still perfectly valid. That's why this approach is universal. It works for every situation, fair or biased, simple or complex. Let's verify the axioms using a concrete example. Suppose we have a biased die where the probabilities of faces 1 to 6 are 0.1, 0.2, 0.1, 0.2, 0.2, and 0.2 respectively. Step 1. Check that all probabilities are non-negative. Heavy checkmark every value is greater than or equal to 0. Step 2. Add them all together. 0.1 plus 0.2 plus 0.1 plus 0.2 plus 0.2 plus 0.2 equals 1. Heavy checkmark step 3. Since the total is 1 and all probabilities are non-negative, this forms a valid probability model. Now, let's find the probability of getting an odd number. The odd faces are 1, 3, and 5. So, P of odd equals 0.1 plus 0.1 plus 0.2, which equals 0.4. And the probability of an even number is P of even equals 1 minus 0.4, which equals 0.6. Everything fits the axioms perfectly. See how neatly the axiomatic approach handles unequal chances? That's exactly why these rules are called the laws of probability. Alright, let's wrap it up. We learned that the axiomatic approach defines probability not through guesswork, but through logic and structure. It uses 3 simple rules: non-negativity, total probability equals 1, and additivity for mutually exclusive events. From these, we derived powerful results like the union formula, complement law, and monotonicity property. We even saw how biased or uneven outcomes still fit neatly within the system. In a sense, Kolmogorov's axioms transformed probability into a branch of pure mathematics, consistent, elegant, and universal. In our next lesson, we'll explore addition and multiplication theorems built directly on these axioms. Until then, keep exploring, keep questioning, and remember, probability is logic quantified.